So any questions? Okay, I'm assuming you guys don't have question. Sorry.
I have a general question.
Okay.
So just going back a little bit, I guess when we talk about deep learning, is that specific to neural networks, or
Yeah.
is that okay?
Actually,
And is deep deep just in response to a neural network with many layers?
Yeah,
Okay.
because actually many machine learning algorithm can be like transformed into a neural network structure.
Oh, okay, sure.
Yeah,
Okay.
because we always have forward and backward computational graph. So here,
Okay.
all the deep learning frameworks are initially specialized for the neural networks.
Sure. Okay. Cool. Thank you.
Okay. Now here are some statistics about Pytorch in academia use. The figure shows the portion of unique mentions of Pytorch in academic conference. As you can see, since the 2017, it increases a lot. Like the conference, like NIPS, SAML, SLR, SCCV, and CVPR are of big influence in the machine learning community. So once again, let's talk about why we choose Pytorch based on functionalities. First, it has augmented tensor operations. Actually, you can treat Pytorch as a GPU accelerated NumPy, and the interface is almost identical to NumPy. So you can really get into it. Second, the automatic differentiation. It allows you when we want to calculate some derivatives, we need to get the analytical form of the derivative. But with automatic differentiation, we don't have to come up with the analytical form. Just use numerical evaluation to evaluate those derivatives. It could be really convenient, and it is a basic building block for almost every deep learning frameworks. Last but not the least, it allows parallel and distributed computing, both on either CPU, GPU, and TPU or TPU. TPU here is Tensor Processing Unit, a specially designed hardware for tensor processing. This feature is really essential for large-scale applications, especially industrial level. And it is implemented in C++, so it can be really high efficient. And here is a picture. I want to show you guys how well GPU acceleration can work. Except the array initialization, all the other operations shows a great acceleration when using GPU. Yeah. Okay, let's get into the installation of Pytorch. If you just want to install Pytorch without GPU, you just need a computer with 64-bit processor and 64 8-bit operating system, as well as a Python library. That's enough for the installation. And if you want to install a GPU version, you must have a compatible GPU with the version of your Pytorch. Here, GPU should NVIDIA could be the only choice because if you want to use AMD CPU GPU, you might need to do some extra work on that. But most of the time, it just doesn't work. And also, you need to install a compatible version of CUDA. CUDA is developed by NVIDIA and provide the interface to the GPU hardware. And CUDA is implemented by using C++, so it is quite efficient. Then, with regard how to install the Pytorch, Anaconda is recommended, officially recommended. Anaconda is just you can treat Anaconda as a package manager of Python. More formally, it is a distribution of Python. It can help you manage Python packages in a really efficient way. And here is a screenshot of from the Pytorch website. You can choose your setting, then just copy the command and install the Pytorch here. So far, any questions? Okay. Next, let's get into the code part. First, I'll just show you how to install the. So can you see my screen?
Yeah.
Okay. First, let's get log onto my desktop here. After installing Anaconda, you can just create a separate environment by conda create some name here. I have created my own. It's called Pytorch. Sorry, I may not. I don't remember the name of the environment. Oh, the environment is Pytorch tutorial. Yeah. And after entering the environment, you just need to install Python. Yeah, I have used. Oh, it has new version, but I will install here, and then you can if you want to install Pytorch with GPU, you must check your hardware. Now here we have NVIDIA GPU here, RTX 2080, and the CUDA version is 11.1. So we need to go to the Pytorch website. Linux CUDA 11.9 and Python conda installation. Here you can also install the Pytorch using pip, but Kana should be more convenient. Here, just copy the command and install it. I have installed the Pytorch, so I'll skip this part here. Okay. So before getting to the code part, you need to get the Pytorch installed properly. Here, all the code I only use CPU version. So if you don't have GPU, don't worry. And after and this tutorial, the code aims to briefly introduce some basics of Pytorch. Basically these 4 parts: the basic data structure, tensor structure, and here I'll introduce the automatic differentiation and computational graph. Third one is the basic building block module, and the last one is the optimizing modules to tell you how to optimize your loss function or objective function. And after install the Pytorch, here you should print out the Pytorch version correctly. Here I installed the latest version 1.8.1. Yeah. For the first part, tensor. Tensor is a widely used basic data structure in deep learning frameworks. In practice, you can just treat a tensor as a multi-dimensional array. There is no difference. Actually, when you use the tensor structure, you cannot feel a big difference between a NumPy multi-dimensional array and tensor. So before, the commonly used vectors and matrices are just 1D tensors and 2D tensors. And for the cube, it's just 3D tensor, and an array of 3D cube is just a 4D tensor, and so on. Now let's get into the code here. Basically, you have 3 options when you want to declare or declare your tensor. The first one is from NumPy here, and the second one is torch.tensor, and the third one is torch.sTensor. The first one is just create tensor from a NumPy array, and the memory of create tensor and the original NumPy array is shared. And the data type, you cannot specify the device here and the data type here. It's all inherited from the NumPy array. Here at the device, we just use the CPU. If you have GPU, you can uncomment this line and try. Here, after declare your own tensor, here we just print original array and declare the tensor by using from NumPy. Here, and I want to change the first element of the tensor. Let's see what will happen. Here, this one is original array, and this is declared tensor. And after changing the first element of the tensor, you can see the original array is also changed because the memory is shared. But for the second one, tensor.tensor, it always copies the data. And it is, if you don't have a limited memory, this method is recommended. You don't have to worry about the read-write overwrite some memory you don't want to overwrite. And here, this function, we can specify the device and the data type. And for the third one as tensor, if the initial value or the arguments is already a tensor, it will avoid copying the data. If it's not a tensor, it will copy the data. Let's see an example here. Here, Pytorch A is already a tensor. So by declaring Pytorch B, so A and B share the same memory. After changing the first element of B, the first element of A should also be changed. Yeah, as you can see here, we print out the value of A is 1. The first element is 1, and sorry, because we use the from NumPy to declare the A, so all three variables share the same memory. The NumPy array also changed. So far, any questions about these three ways to declare your own tensor? Okay, let's get into the next part. So first, we need to know what is a computational graph. Actually, computational graph is defined as a directed graph where the nodes are mathematical operations. Here is a really simple example of computational graph. Here, the pink node is not the node of the computational graph. It's just some associated variables to the operators. Here, the green ones are the nodes of the computational graph. As you know, in neural networks, first we do the forward pass to calculate the output of the neural network or the loss of the neural network. Then we conduct the backward propagation to calculate the derivative or the gradients of the weight and update the weight accordingly. And automatic differentiation is a set of techniques to numerically evaluate the derivative of functions specified by a computer program. So here, before we use analytic form of the derivative, here we just use the technique auto differentiation to evaluate this value. And based on that, and together with the computational graph and the chain rule, we can get the derivative for each variable here. So you can see the first figure is for the forward pass, and the second figure is for the backward pass. So any questions about computational graph and automatic differentiation? Okay. Now let's get into the code part. Here, I just want to show a really simple computational graph built by Pytorch. Here, we still use the CPU here. And here we need a tensor. Here we just declare 3 tensors. WXY. W and Y are dummy input and output. And W here is the weight tensor. Here we just declare a 10 by 1 weight tensor, device on CPU, and requires gradient. In early versions, you may find a specified class for tensors with gradient. It's called variable, but it's deprecated in the current version. So you can just use tensor with gradient to represent the variable. So for the forward pass, we need to build the a computational graph. First, we just do the inner product, and then we calculate the difference between predicted value and the real value, then square, and we calculate the square sum. And here, by printing it out, here we can see that A, B, C, and L are all tensors. And here we have an extra attribute for that. It means it represents a node in the computational graph. If we set the flag requires gradient false here, let's see what will happen. Yeah, there is no computational graph anymore, and all the calculated tensor are just tensors. No gradient value, no gradient function anymore. Also, as you can see, we build the computational graph by here. By doing this, we can just create the computational graph. But in TensorFlow, this kind of programming style is called imperative programming style, because we created the graph dynamically. But in TensorFlow and Theano, we need to use symbolic a variable to build the graph first, then feed the data into those placeholders. Then we can get some results. That's different. That's the difference between imperative programming and symbolic programming. Here, this is just the forward pass of the graph. Now, with auto differentiation, we can just use this function backward to calculate the derivative of each tensor. Here, let's say the gradient of the tensors. Here, the gradient of W. Here we can just use the grad, the attribute grad, to show the gradient of that tensor. Because we, by default, the requires gradient for tensor is false. So for X and Y, we can't get its gradient here. So it's none. And sometimes there are two important flags in this function, backward function. First one is retain graph. Usually this flag is false, and the graph will be freed immediately after the backward pass finishes. But sometimes we may want to do some further calculation based on the current graph, so we can set this retain graph to be true. What if we call backward again with retain graph as false? it will cause this kind of error trying to backwards through the graph a second time, because the graph is already frayed. It is already frayed, so we can backwards through the graph again. And here the create graph means we want to use we want to add the calculated gradients as a new node into the graph. If we set it to be true, the newly calculated gradients will be treated as a new node in the graph. If this flag is set to be true, this flag will automatically set to be true. And here with regard to this part, we may have two common mistakes. The first one we just mentioned, try to backwards through the graph a second time with return graph set to false, or the create graph set to false. And the second one is to forget to set the requires grad flag if you want to calculate the gradients of some tensors, but you forgot to set the requires grad to be true. It would be a problem. And now, any questions about this part? Okay, I'm assuming all you guys understand what I just said. The next one is the module. Module is a very basic class in Pytorch to build up your own model. And module can be different types of layers or activation functions or module containers. And the modules can also contain other modules, allowing them to nest them in a tree structure. There are many predefined layers in Pytorch. Here, I just gave a simple example about CNN here. In Pytorch, all these layers are predefined, so you can use them very conveniently, like the convolutional layer, pooling layer, and fully connected layer. It's just a linear layer here. Also, it also has some LSTM cell and RNN cell. First let's see some really simple examples about how to build a module. Here we just want to build a really simple neural network, but first we need to build some basic layers for the neural network. Here we just define a really simple linear module, linear layer here. It's called self-linear. For the self-linear class, we for the module class, besides the initialization, it only has one important function. It's called forward. It defines how this module do the linear forward pass with input x. Here we just do the simple linear operations. That is inner product and plus the bias. Here in the module, we need to register the parameter. Here we don't have to specify the request grade for the parameter, because it is by default need to be the required gradients will be set to be true, and it will automatically registered in the module. So module has another function called parameters. You don't have to override this parameter. I just try to tell you guys there is a function called parameters. You can use this function to collect all the parameters within this module registered using parameter function. Here we define the weight and bias, and for the forward function, we just output its linear linear result. And for the network, it's also a module. And here we also define the forward function here. And we define the activation function ReLU here, and we should pay more attention to how we manage our modules in another module. Usually for list, we tend to use Python list here, and a dictionary of Python dictionary here. But if you want to get your parameters in the module properly registered, you must use module list or module dictionary. Because these two classes are also module class. So when you call the parameters, the module will first search all the modules in your module and collect the parameters of all the modules in each module. And here we also define the layers, the network layers. The first element is the input dimension, and the last element is the output dimension. And between are the dimension of the hidden layers. Here we just create a module list for fully connected layers, just linear layers, and we go through each element of the layers and create a linear layer for the network. Here, I forgot to introduce the parameter of the linear layer. This one is input dimension, and this one is output dimension. And X here usually should be n by d tensor. And d here just the n the number of features of the input. And here the output should be n by n output. And with the night, and we can create our own network. Here we just set the layers to be 1. The input dimension is 1, and output dimension is also 1. And we have 3 hidden layers with dimension 10. And we create our own neural network with our net class. And here we first print out the model parameters. As you can see, all the parameters are properly registered, so we can get all the parameters of our model. Now here we can see the first layer. For the first layer, the weights and the bias. Second layer, weights and bias. Third, weights and bias. Weights and bias. That's really easy. And why we use module? Because the first advantage is that it is really easy to collect all the parameters if we don't encapsulate our model in this way, for a really deep network, there should be hundreds of thousands of parameters. If we do collect those parameters manually, it would be really painful. And the second one is we can translate between different devices by just calling model CUDA. This command, this line just tell us to translate the model to device GPU, and we can also translate the model from GPU to CPU by calling this. It will automatically translate all the parameters in the module from one device to another. And the third advantage is that we can easily save the model by using module. Here, a module have a state dictionary. Each module would have a state dictionary, and by calling this, we can get the state of that model. And with torch save and torch load, we can easily save and load the model. And here, there should be only one common mistake. It's just that use the Python list or the Python dictionary instead of module list, module dictionary, or parameter list or parameter dictionary. Only with these containers, the parameter can be properly registered. So any questions about this part?
For the upcoming assignment, are we going to be expected to kind of create our neural network using these libraries and stuff?
Sorry, can you repeat that?
For the upcoming assignment, are we going to be using Pytorch to create our neural networks?
No. You should do. You should first derive the derivative analytically and do it in a low level. Yeah, you are not supposed to use auto differentiation tools.
Sounds good.
Okay. But if you use Pytorch, the assignment is just too easy for you. And here, yeah, any question about the model saving part? Okay. And so far, we should be able to build our own model, but that's not enough because all the machine learning algorithm should finally become an optimization problem. So we need also take optimizer into consideration. So again, also that example above, but here we try to after the forward pass, we need to set our own objective functions, and with auto differentiation, and we need to update the corresponding with vector of with tensor with the gradient. So here in Pytorch we have this module called Optim, and in this module we have predefined optimizers like stochastic gradient descent, ADAM, LDAT delta, and LDAT grid. For these three algorithms, the learning rate should be changing for each iteration. And a stochastic gradient descent is of fixed learning rate. Here again, we define the same network and we create a dummy input and output, and we declare our optimizer using SGD. And here for each optimization algorithm, you should feed the model parameters as one argument to tell the optimizer which parameter to update. And here usually it has a argument called learning rate here. And we just run 30 epoch. In each epoch, we need first to zero the gradients of all the parameters, because the gradients will be accumulated if you don't zero the gradient first. This step is very important. Don't forget to do this. Usually, when we write the code, we just first do optimizer zero grade and optimizer step first. Then we just fill our own code between these two lines. And for the forward pass, we calculate the sum of sum of square errors, and by calling backward, we can calculate the gradients for each parameters in our model. And with optimizer, it can adopt different algorithms, adopt different learning schedules for about how to update your parameters with calculated gradients. So this one, if you are interested, you can get into this function and see how different algorithm update the parameters. And for this part, any question? Okay. Now let's look at a relatively complete learning procedure with sign regression. Here, I just create some data set for the learning and try to learn some good results here. And the network is still the same. And here we set the training number. Here the training sample number as 100, and the testing number is 20. The first type of data is kind of for interpolation, and the second type is extrapolation. Let's see the first type of data first. And first we create the input using NumPy random uniform distribution function. Here we just create 120 points uniformly between -5 and 5, and we apply the sign function over the input points and get the output, and we split the training set and the testing set. Here we create a neural network with 2 hidden layers of size 40, and here we use a DAM. A DAM is also a stochastic gradient descent algorithm with momentum, so the learning rate should change for different epoch. Here we declare these two lists to collect training errors and testing errors. And the batch size here we set as 50. It's a little bit too large for 100. And here we just calculate the batch number. Here is a really simple way to calculate the batch number without using any other functions like floor or ceiling. If you are interested, you can see how you can try to remember this trick. Here we train the data for 1,000 epochs, and in each epoch we just get our batch and send it to the model. Oh yeah, I forgot to mention this. By doing so, we just call the forward function in our module. And here the loss function is still the sum square error, and we do the backward pass and optimize and update the gradients, update the weights accordingly. And here we have this one, the torch no gradient. Within this context, there would be no computational graph created within this context, because we just want to evaluate our the performance of our model. We don't want to create any other nodes anymore. And here we just calculate the training error and the testing error. Here is just the RMSE. Item is to extract the element of the tensor as a NumPy or a Python number. Here, after the training, we just calculated the predicted output of the current model. Here we are some plotting code we just plot two figures. The first one is for the training and testing error, and the second one is for the training and testing and prediction points. As we can see, here first let's try to use our self-defined linear module here and see what will happen. As you can see, the training and testing error is really high here, because here is the scale of the y-axis changes, and let's see what happens if we use predefined linear module. Yeah, the scale changed to smaller than 1, and the only difference between self-defined linear and the predefined linear is the initialization of the weights vector and bias vector. So it means the initialization matters a lot in your training. Yeah. So here are some tuning tips for you guys, and the first one is just the initialization, and let's try the second type of data to explore the extrapolation performance of neural network. As you can see, for the performance for extrapolation is really bad. Here, the blue points are the training points, and the orange points are the ground truth for testing points, and the green points are prediction points, predicted points. And you can see for extrapolation is almost a linear extrapolation. Here we use the 10H activation function here. Let's see what happens if we use the ReLU. Yeah, it could be even worse. So the second tip for the tuning is we may try different activation functions to see how that will improve our learning performance. And the third one is the learning rate. Actually, for every variable parameters in the learning part can influence the learning process a lot. Even if we change the batch size here, the learning result for the first kind of data should change a lot. Yeah, I don't remember the previous results, but the testing error was under the training error in the previous setting, but now it's above the training error curve, so it differs. And after that, you may need to develop a good habit about saving the model, because you'll never know if it is already a well-trained model or not. So you can save it for later use. And for a complete model saving, first you need to save the training parameters. Here I only take the epoch for examples. You may need to save the batch size, input size, output input testing size, training size. Also, you need to save the model parameters here just by calling the state dictionary, and also the state of the optimizer, because for them it has some scheduling parameters, and it has its own state. So you need also extract the state of the optimizer and save the model. And here is just the path for the saving model. Okay, now we have gone through all the parts of the codes. So you should have a better understanding how Pytorch works, and you should be able to, you should be able to build some simple models using Pytorch. Have fun. And let's switch back to the slides here. Also, for the code part, any question? Okay. So when it comes to GPU, you can always use your gaming PC as your lab station to train your model, and you can also use Google Colab. The Google Colab has free GPU resources, but many people want to use those free resources, so it could be really competitive, and you may not get a good quota, and it might be slow as well. And also you can also resort to University Center for High Performance Computing. I don't know if they have free resources for GPU, but you can have a try. And after during or after training the data, you could also use these 3 tools to visualize your model or the training results. Pytorch summary is a very good tool to tell you how your model is, and can list many details about your models even before you start training. And it's very easy to use. And the second one, Wisdom, is a really powerful visualization library for you to check the outputs or the intermediate outputs of training layer of hidden layers, how it would look like. And for the TensorBoard, I have never used TensorBoard, but it seems to be really powerful and interactive. Maybe here you can try. Maybe you can set different settings by using TensorBoard and see what your learning curve would look like. So far, any question? And that would be all. Thanks for any question before I end the lecture. Okay. So thanks for your attending, and have a good weekend.
Thank you.
Thank you.
Hi, Professor, are you there?